All right, guys, so today what we're going to look at is an example of a simple machines problem with multiple parts. So before we do that, just want to reiterate the idea that a machine the idea is it allows us to be able to do work using potentially less force. As we were talking about, you're able to trade off force and distance so that using more distance and less force gives you the same work as a big force and a small distance. All right, so if you look at the question here, it says a person tries to lift a 150 kilogram object up to a height of 2 meters but cannot complete the task. The person decides to build a ramp that is 8.0 meters long and push the object up the ramp. How much force would the person have needed to exert without the ramp? What minimum force would be required to push it up the ramp? What's the ideal mechanical advantage of the ramp? And if it actually takes 490 newtons of force because of friction, what's the actual mechanical advantage? So remember, no machine is perfect. There's always a little bit of friction, even if it's a pulley or a ramp or whatever it is. So the actual mechanical advantage and the ideal mechanical advantage never quite match up. And we'll talk about how that relates to efficiency later on. Okay, but the number one thing that we need to understand is this idea that the amount of work in and the amount of work that you get out of the machine ideally would be exactly the same. So we start by saying that the work in is equal to the work out. And the way I'm going to write that is like this. I'm going to say force in times distance in equals force out times distance out. All right, and you want to keep in mind that what's in is what you do. It's what the person that's using, the user of the machine, does, is the input. What the machine does is what we call the output. All right, so that's over here. All right, in part A, how much force would the person have needed to exert without the ramp? Well, if you think about the object, it's a 150 kilogram object. So let's draw that over here. If we want to lift up that 150 kilogram object without the ramp, we need to be at least as strong as gravity. So the force of gravity on any object, if you remember, we did this last chapter, the force of gravity is mass times g. So that's going to be 150 kilograms times 9.8, and that gives me 1,470 newtons. So if I'm going to be able to lift this object upwards, I'm going to need to be able to exert at least this much force. All right, so I'm going to write that in for part A. At least 1,470 newtons, because that's the weight of the object. And if we want it to be lifted, we have to fight against gravity to do that. Okay. Now, in part 2, it says what minimum force would be required to push it up the ramp. Well, if we use the ramp, we're not going to need to exert as much force. If you think about using the ramp, now we're taking the object and we're going to push it along the slope. So it's going to rise 2 meters high. But the distance that we push it is further than 2 meters, obviously. We're going to push it along this slope. And this is 8 meters in length. Okay, so what the person who's using the machine is going to do is apply some force over a distance of 8 meters. So let's say F in times 8 meters equals the force that the machine exerts is lifting the object. That's the answer that we got earlier, 1,470 newtons, because it's going to move up the ramp. So this is 1,470 newtons, And the distance it's going to move is that 2 meters along the ramp this way. Okay, so we can solve this for the input force if we divide both sides by 8. So if I divide this by 8 meters, and I divide this also by 8 meters. So we can put this in our calculator. Let me grab my calculator, and we have 1,470 newtons times 2 meters. So 1,470 times 2 divided by 8. I get 367.5. So the input force equals 367.5 newtons. That's my answer to part 2. Okay. Number 3 says, what is the ideal mechanical advantage of the ramp? Now you might remember in the video that we watched that the ideal mechanical advantage is the output distance divided by the input distance. So let's write that down real quick. The ideal mechanical advantage equals the input distance over the output distance. I said that backwards the first time. Input distance over output distance. Okay, so our input distance is 8 meters, and the output distance is 2 meters. We get 4. So what that means, when we say the ideal mechanical advantage, what we're saying is, how much does the machine multiply our force by? It multiplies our force by 4. All right, I only need to push with 367 newtons to get an output of 1,470 newtons. All right, so that's our answer for part 3. Okay, and then the last piece of this, it says if it actually takes 490 newtons of force because of friction, what is the actual mechanical advantage? All right, so let's erase this piece right here and go over that. When we want to know the actual mechanical advantage, we have to look at the forces. Okay, so what we'll do is we'll do the output force divided by the input force. Okay, so actual, whoops. That's too thick. Let's try this one. Actual mechanical advantage equals output force over input force. So how much force did the machine exert versus how much force did you exert? All right, well, the machine is lifting this 1,470 Newton object. So this is 1,470. And the amount of force that you actually had to push with is 490 Newtons. So if we divide those two numbers, we get the actual mechanical advantage, and it turns out to be exactly 3. All right, so the actual mechanical advantage is 3, not 4. And the reason why it's lower is because the ramp does have friction. It's not a frictionless ramp. So not 100% of the energy that you put in is going to be turned into moving the object. Some of it's going to turn into heat as a result of sliding along that ramp. Okay, so to find the force we would need to lift the object, we used mg to find the weight. Then we used the idea that the work in has to equal the work out to calculate the force required. And then we calculated actual and ideal mechanical advantage using the equations here. So ideal mechanical advantage is distance in divided by distance out, and actual mechanical advantage equals force out divided by force in.